Okay, so we are on to the applied questions for Chapter 3 of An Introduction to Statistical Learning, second edition. So before you run this, or if you're going to use any of this code, you need to make sure that you've installed and loaded the ISLR package, which is an R package that comes with the book, or it doesn't come with the book, but it's associated with the book. So here's our question. And so this is, I think, one of the first times we actually get to start using some code. What have I done here? Okay, so we are going to be using a data set that's part of the ISLR package called Auto. It's the Auto data set. And we're going to run linear regression on it, okay, in R. I'll make a separate video for Python. Okay, so we are meant to regress the variable MPG, or miles per gallon, as the response variable, and we're supposed to regress that on the predictor variable horsepower. Okay, and then we're going to look at all sorts of different things about it associated with the questions here. We're also going to plot. We'll get a regression line out of this, and we're going to plot that in part B. And then in part C, we're going to use some diagnostic plots that will help us determine if our linear regression is adequately fitting the data or not. Okay. So first, let's just run the regression. So I'm loading the data set, Auto, okay? And now I'm going to create my regression, and I'm calling it MPG_reg for regression. And for normal linear regression, the command is LM for linear model. And so I'm regressing M on horsepower. So this little tilde means regress this thing as the outcome on this predictor or set of predictors. And then I'm specifying that my data is coming from Auto, from the Auto data set. And that's going to run regression. And then I'm going to get a summary of that regression here. So when I run that, let's walk through this. So first the call, so this is the output. The call says, okay, this is what you ran. Okay, that's the command that you ran. This is some information on the residuals. We won't talk too much about that, because a better way to think about these is in the residual plots or the diagnostic plots that we'll use at the end of this question. And usually what's most interesting is this stuff here and maybe here. So this is the coefficients that are estimated for our linear regression, the alpha or the intercept, as well as the beta term for horsepower. Okay, and so we get the estimate for these values, the standard error of those estimates, the t-value. So on a t distribution, we won't go into it here because the book doesn't go into it too much. And the p-value that is derived from the t-value. Okay, so often, usually the thing that people are looking at is the p-value and the estimate to get a sense of what's going on here. Okay, what can we glean about the relationship then between horsepower and miles per gallon with this output? Okay, so maybe one of the first things is that the p-value is very low, which suggests that there is strong evidence for a relationship between horsepower and miles per gallon, right? Very low p-value. Okay, and then with the estimate, we can say that roughly what is going on is that miles per gallon is decreasing, because of the negative sign, is decreasing by 0.16 miles per gallon, or whatever the units are, for every 1 unit increase in horsepower. That's what that would mean right there. And then there would be a standard error associated with that estimate. Okay. So anyway, that is part. So that addresses all of this from part A. And now we're asked to predict, or we're asked to find a predicted value for a given horsepower, as well as 95% confidence and prediction intervals. Okay, so one way that we could find the prediction for 98 horsepower is we could just take this is what our regression would look like, the alpha, which was the intercept, plus the beta times horsepower, right? And remember the LM function estimated, even though this says horsepower, that is a piece of data. It is estimating the beta coefficient for horsepower. Well, we could just plug the estimate values we got in for that, and we would get this. Okay. We could also calculate that in R. Okay. So with this, so that's pretty close, just minus maybe some rounding error. Now, the way that I'm doing this is I'm taking coef, so this is a command that returns the coefficients from your regression, okay? And I'm taking the first one, which is intercept, plus the other coefficient, the second coefficient, which is horsepower, and then multiplying that by 98 horsepower, okay? But the easiest way to do it, and that's why we use statistical software, is because we don't want to do everything by hand, is to just use the predict function, okay? And so I'm going to predict this, right? I'm going to use this model, and I'm going to use this as my predictor, right? So I use data frame horsepower equals 98, okay? And there's different types of intervals. We'll see another one here in a minute, but we are using the prediction interval. And this is going to give us a 95% level of the prediction interval. If that doesn't make sense just yet, wait till we get to the confidence intervals. But anyway, we see that the prediction is 24.46, which we've already calculated in two other ways. And then we get this interval, the lower and upper interval. Now, what's important to recognize here is that this is a prediction interval. Okay, and I'll talk about, next we'll talk about a confidence interval, and then I'll talk about how the prediction interval and the confidence interval differ. Okay, so now let's predict the confidence interval. So I'm going to use that same code that I used here, but instead of interval equals prediction, I'm going to use interval equals confidence. Okay, so I'm going to get a confidence interval. So I'm going to run that. Notice I get the same fit, but now I get a different interval. Okay. So I get a much more narrow interval. So what's going on here? What's the difference between these two? Okay. Well, the prediction interval is using the standard deviation of the estimates. Okay, and it is saying, okay, when I'm going to predict a value given 98 horsepower, and even though the average of those predictions is this, I wouldn't be with 90. If I go out the appropriate amount of standard deviations to represent 95% of the standard distribution, then I wouldn't be expected, or I wouldn't be surprised to see a value from here to here. Okay. The confidence interval, on the other hand, is using the standard error, not the standard deviation. And the standard error is smaller than the standard deviation. In fact, the way you get the standard error is by dividing the standard deviation by the square root of n, right? So it's going to be smaller than the standard deviation, and it refers to the mean of the prediction. So it says that the best guess for the mean of the prediction is here, okay? But other mean values with 95% confidence lie in this range, right? So whereas the interval for the prediction is saying this is where the prediction might lie, the confidence interval is referring to the average of predictions, if that makes sense. I'm not saying that very eloquently, but I hope it makes sense. So the next thing that we want to do is to plot the response variable and use the function abline to plot the regression, okay, or the least squares regression line. So I'm going to plot here. Let me cancel that out. I'm going to first plot the data MPG against horsepower. Okay, so this is the data, right? So I'm plotting MPG. That's my response variable. It goes on the y-axis. And I'm plotting it against horsepower. That's my predictor variable. It usually goes on the x-axis. Okay, and this is what the data looks like. And then when I plot my AB line against that, right? So I just do AB line, the regression that I'm taking this from, and I'm going to color it red. Okay, and this is what we get. Okay, and so now in the last part of the question, we want to determine, or we want to make some judgments here about how well this line is fitting the data. Well, right now, just by looking at this, it doesn't look like the line is doing a great job. We see kind of this kind of curvy shape to the data. It seems to be following some kind of nonlinear thing, but the line obviously is, well, it's linear, and it doesn't seem to be doing a great job. But there's more plots that we can use to start to make better assessments. And so I do that with the plot function, and I just plot the regression that I'm using, and I get a series of 4 plots here. Okay, and they're all telling us something about the fit of the model. So let's go through these one at a time. There's other resources about this. This will be just kind of a cursory overview of it. But the first plot, the residuals versus fitted. So here I have the fitted values from the regression, and then the residuals, right? So every fitted value is going to be different, or most fitted values are going to be different than the actual values, and that amount is called the residual. And one of the assumptions about normal linear regression is that these residuals will be evenly spaced throughout for all values of predictor variables and for each fitted value, etc. But we see that as we go further along the x-axis, there seems to be more spread, and also it doesn't seem to be that there's any. It seems that the residuals themselves are following some kind of nonlinear pattern, and so this suggests that we are violating at least one or two of the assumptions of normal distribution, or of normal linear regression. We get similar information from this plot. To be honest, I don't really use this plot very often, but we're getting similar information there. Again, we have fitted values, now we have standardized residuals. So, so the next plot, the QQ residuals, the second plot, is plotting quantiles of a normal distribution and the residuals. Okay, so a normal distribution, the residuals should fall right along this line, this linear line, this straight line. And when we start to see deviations from that, as we do here, it suggests that maybe a normal distribution is not capturing the data very well. Okay, already talked about 3. And then the last one here is residuals and leverage, and this takes a little bit of understanding about linear regression and linear algebra, really. But roughly what's happening here, so the further out I go on the x-axis, and the farther up I go on the y-axis, so as I start to get into kind of these regions, right, it means that observations that correspond to those dots there exert more influence on the fit of the linear regression, right? So this point right here, for instance, has more say about the fit of the linear regression than these points do here, okay? If we have a lot of these values, this suggests a few things. It suggests that maybe some of these values are in error, and we should check our data because maybe these values were recorded mistakenly. We might call these, if they're not mistaken, they might be called outliers. And what do we do with the outliers? Well, it kind of depends. A lot of people will just throw them away, but that's a little bit hasty. What this really tells us is that the assumptions that are embedded in our normal linear model are not doing a great job with our data. And so taken everything together, given this plot and the rest of the plots and everything we've talked about, it seems that normal linear regression is not our best option, although it's all that we know right now. But it may not be our best option here. So all of these plots are really pointing to the idea that that the data is not well approximated with a normal linear regression.